Matt McGovern, go for it, my friend.
Cool, thank you. I will share my screen. Make sure good. Share that. Uh,
There it is. It's working.
yes. I've got the slideshow. You can see it as a big slideshow.
Yes.
Perfect. All right. So if you've been along to a few of these, you've heard me before. I teach at North High School in the Hawke's Bay. I want to explain these energy bar charts. Hopefully they're pretty intuitive and this won't take that long, but I've got some examples and then point you in the direction of a bunch of worksheets you can just roll straight out into your classroom. I know some of you already started teaching the energy unit. Kerry, I don't think she's here yet, certainly has it over at New Plymouth, and she's finding these very, very useful. So hopefully once you get started with them, you'll find them as good. So we'll just quickly go, why energy bar charts? Because they're probably quite new to most people in New Zealand. How to do them, how to simple ones, how to do harder ones, and how you can put them in everything in this whole topic. So the standard clearly says that evidence about energy is in written accounts and representations or calculations. And I know most of the time, historically, certainly in this country, we talk about the energy forms and then we do the calculations, but we haven't had as much concentration on the representations of energy. And around the world, there's three main types of representations for energy. So one's an energy pie chart, and that's just a pie chart's divided into segments to show what proportion is each type of energy. So this is a ball thrown up in the air. It starts with kinetic energy. As it gets higher, it loses some of that kinetic energy to gravitational. It gets all gravitational at the top, and then it goes down and flips again. The second type is an energy bar chart. So we always look for energy bar charts at two states, an initial state and a final state, and we also describe the system. Energy bar charts are also called, if you look them up online, energy bar charts, you'll find heaps, but they're also called LOL charts, LOL, because the first axis of the initial state looks like an L, where you write the system looks like an O, and where you write the axis of the last graph's an L as well. So LOL, LOL charts. The kids, if you ask them to draw a LOL chart, just straight away we'll put down the big LOL, and they'll start from there, so they'll get used to doing that. And the third type is Sankey diagrams, which you have seen a bit as well. Each of these have their own pros and cons. So it's not saying that in every situation, energy bar charts are the most superior, because certainly Sankey diagrams show very complicated things very, very well. But the issue at this level, at year 11, that why we'd choose in these SLOs, these student learning outcomes, because the SLOs are all about focusing on what needs to be taught and what needs to be examined on just one of them, and why that one, why the energy bar chart. There's three reasons. One is this idea of systems, one is how kids draw them by hand, and one is this idea of energy transfers. So the actual standard has mentions physical systems a lot, and because of that, it makes sense that we are teaching our kids to explicitly choose a system and get used to doing that. And with energy, it changes everything depending on what system you're choosing. And choosing the system is inherent in doing these energy bar charts. You saw the circle in the middle is where you write down your system. And we'll go through an example of that. We'll go through many examples of that pretty soon. Hand drawing them. So here's I've got a situation where a person's kicked a ball. In the initial states, the ball's just leaving the foot. It's got some speed, and then it's up high. It's still got some speed, but it's probably got not as much. So I'm going to give you three badly drawn examples. They're still, the kid's got the right physics idea, but I've just exaggerated how badly you can draw them and show you what happens. So if you get a pie chart and a kid just draws some circles, you can get them being different sizes, right? And that's an issue straight away, because the only important thing when teaching energy is conservation of energy, right? Energy doesn't have any power to explain how things are happening or why things are happening unless you invoke the idea of conservation of energy. So a badly drawn pie chart like this looks like the energy's growing, but the kid's just focusing on getting the labels right? Because that's all they've been taught. And if there's no focus on that. Here's a badly drawn energy bar chart. You can see on the right-hand side, the energy bars are different heights, but even if you draw it badly, you've got 1, 2, 3, 4 energy bars on the left and 1, 2, 3, 4 energy bars on the right. So you're still, even with a badly drawn diagram, invoking this idea of conservation of energy. And then we've got a Sankey diagram. Hand drawing Sankey diagrams is a nightmare, all right? And so giving kids computer drawn Sankey diagrams and getting to explain it, okay. But drawing them, it just real nightmare in terms of getting conservation of energy right. So that's the second reason, is because in the end, kids are going to hand draw them. I can't imagine us going to some sort of computer exam and even using computers every day in physics classrooms. The last one is energy transfers. Now, this is a complicated energy bar chart, and we're going to talk about these energy transfers. But this is it, even for me, who's done advanced degrees in physics. It wasn't until I got onto these energy bar charts that I could understand the concept of work and heat and electrical energy beyond work equals force times distance. So actually seeing it moving energy into a system or pulling energy out of a system was really, really powerful for me. So we'll go through an example of that because this is quite a complicated one. But there's those 3 ideas that make these energy bar charts perfect for learning about the concept of energy at this level, which is we're going to be describing the system. That's so much easier to hand draw and get conservation of energy right. And we can explicitly teach these energy transfers like work, which has only ever been examined as, can you calculate force times distance? And now we get a chance to actually see that kids understand that means putting energy into the system or taking energy out of the system. So there's plenty of research papers on how effective energy bar charts are, and they sort of all sum up their findings in the sort of the same way, that the energy bar charts, they force students to qualitatively reason, so actually reason with the concept of energy before they go into the calculations. And one of the biggest things in all the physics education research, one of the issues with kids learning physics is that they see physics as, what's the formula? I've got some numbers, put it in. And they've got no idea of the concepts that are going on in the background. So experts, then there's lots of papers that have interviewed and figured out how experts think when they are looking at problems. They'll look at problems and they'll get all the concepts right first before they start saying, okay, now I'm ready to start using equations. So we're kind of teaching kids to do that by using this energy bar chart. Get the concepts of the energy right first and then move on. Secondly, energy is so abstract, right? And so it's making it visible to them, but also it makes their thinking about this really abstract topic visible to you. And I always thought, well, hey, these things are going to be useful for the kids, that's great. But seeing them draw it and being able to instantly look at their drawing and say they understand things, they don't understand things, I can ask them questions about it, it's so, so powerful. So how do we go on to doing these energy bar charts? We're not just going to go to step 4 and draw them first. There's 3 steps first, and they are to identify the system. So the definition I give to kids right the way through high school is a system that is the objects that you care about in this problem. Could be one, most of the time it's one object, sometimes it's a couple of objects, but we just got to make sure we write it down so everyone knows what we're thinking about. Identify the initial and the final state. So you say you drop a ball and you say, okay, let's do an energy problem for that. It seems obvious that the initial state's when I let go of the ball and the final state's, a millisecond before it hits the ground. There's been a couple of really good papers where they interview kids and they've got no idea of why you would choose those as the initial and final states. So we're going to get kids to go through this process and make sure that they choose those, and you can see them choosing initial and final states. And then identify the energy forms for those. So and then we go on to the energy bar chart last, but because these first 3 are so important, the first worksheet I've made, which is up in the NZIP material, instead of doing what I used to do as an energy circus, and the kids would go around the room and they'd look at a microphone and say that's sound energy, and they'd look at a ramp and say that's gravitational energy, and they just look at a whole bunch of things and label them. Is now the energy circus I've got is a bunch of material, or you can do it as pictures. The kids have to choose a system, so this will be the cart, choose an initial state and a final state, and we debate what the initial state and the final states are. Okay, you'll be surprised how many kids will say the initial state of the car's at the top, not moving. The final state, the car's rolled down the ramp and rolled to a stop and not moving again. And it's not really that interesting to look at that. So getting them to choose and debate these initial and final states, and then talk about the energy forms. When it's at the top, it has gravitational energy. When it's just at the bottom, it has kinetic energy, is really powerful. So there's a bunch of pictures and exactly the same questions for them to go through and answer for that. So they get in the habit of choosing an initial and a final state and going through that process of choosing the system and writing things down. So a cup of hot cocoa, what's the initial and final state for that? We can just say the initials, it's hot. The final state's 5 minutes later when it's lukewarm, right? Bungee jumper, left the block. Final state is fully stretched out, but not moving. So I've got suggested answers for these as well. So if you get in the NZRP site and you want to see what the answers are, I've got them up there. All right, so now we've gone through these first three things: identifying the system, which is the objects you care about, the final initial state, and the energy forms. Now we just draw the energy bar chart. So we've got this example of kicking a ball. So the ball has left the foot, it's moving, and it's up high. It's still moving, but probably not as fast. So the energy bar chart makes you go through this process, right? It's got an initial state, it's got a final state, it's got a system. So those are the questions we were asking before. So the system in this case is the ball. I'd identify what type of energy it has. Well, it has kinetic energy, and then in the final state, it's kinetic and gravitational, and then you put the energy bar charts on, the energy bars on. So give it 3 bars of kinetic, and I'll give it these bars at the end. Right. So the first thing is conservation of energy. There's 3 bars on the left, 3 bars on the right. Pretty standard. Could I have given it 4 bars? Yes, because there's no units here. I'm not trying to do calculations with it. It's about getting the idea of conservation of energy. So I often do these with mini whiteboards, or get a kid to put it on the whiteboard at the front, and then talk about how someone will say, why didn't you choose 5? Or why didn't you choose, why aren't these equal? And we don't know that until we do calculations. But at the moment, we're just getting the general qualitative idea, or the concepts right, that it has all kinetic, and that moves into some kinetic and some gravitational. So it's going slower at the top because it's lost some of its kinetic energy. It's a simple bar chart. So from that, remember, this is the step between an abstract idea and abstract equations. You can now write an equation. Now this one's a little bit complicated because I've got initial and final here, but I just say I've got some kinetic energy, and that turns into, which is equal sign, some final kinetic energy plus some gravitational energy. And if you wanted to, you could give numbers to that and get kids to calculate it. For really advanced kids, eventually they're going to be doing half mv squared and mgh for that as well. Right, so we're not just asking kids to say, write down a formula. We're doing this intermediate step with the energy bar chart to help us form the formula. And you can see when they don't have the formula right, a step backwards, what have they got wrong that makes it like that? So the worksheet examples are set out like this. This is just a copy and paste on the worksheet example. I force the kids to talk about the system, the initial state, the final state. Then they do their energy bar chart. Then there's room to write down their energy. And the questions are a cart going down a ramp. I think the second question is, okay, now consider this very same cart, but the final state is halfway down the ramp. So then they have to make a decision on how is that different than the first one. There's a question of a cart being pushed by a spring up a loop-to-loop, and there's a second question where it goes halfway up the loop-to-loop. You've got the bungee jumper again. There's a few other examples. Then there's some examples where I've given the energy bar charts, and the kids have to work backwards and say, what could the situation be where it has lots of gravitational energy at the end, but not as much gravitational energy at the start, and it's lost some of its kinetic energy. It's turned into gravitational. So I have to name a system and then work backwards and come up with a question, or draw a picture of what's going on here. Here we've got one that has lots of gravitational energy, which turns into kinetic energy and some thermal energy as well. All right. So far we've looked at simplest ones, and one of the ones we saw early on was a more difficult one, and we're going to look at that now. So this is the kicked ball that I had before, but if you looked before in the corner here, the kicked ball had left the foot, it has velocity. So it has kinetic energy, here's the bar chart for it. So even me talking to you now, I can use this to visually show what I'm talking about. It has kinetic energy, and then it goes up to some kinetic and some gravitational. This new situation I want to look at is the same situation, but before the ball is kicked. So the ball's sitting stationary on the ground. So if we look at that, the initial states, the system's still the ball, just looking at the ball, right? And this is what we had before, so why don't we just start with that? But it has no kinetic energy, it's not moving. So no kinetic energy for the start. And final, it's exactly the same. It's up high, so it has some gravitational energy. It's moving, so it has some kinetic energy. But that doesn't balance in conservation of energy. Didn't we learn in class, sir, that energy can't be created or destroyed, right? Isn't energy always the same? So this is a situation where energy is being put into the system. Okay, so now we're looking at how a scientist thinks of energy. These are energy transfers. So you can add these to energy bar charts to make them balance. So the energy obviously came from the person, right? And it must have been 3 units because that's how much energy we had at the end. And it's come from outside the system, the ball, and it's been given to the ball by the person. And the type of transfer, it's not electrical, it's not heat, it must be work. They've applied a force to the ball, and that's given it its energy. So that's my definition of work. Okay, I don't actually give a definition of work in terms of words, energy leaving or entering the system. I give a definition of work visually and show the energy coming in. Now you could, if you want to, you could say the system's the ball and the person. If that's the case, energy didn't come in from outside, it came from the chemical energy in the person, and you'd have a bar for chemical energy. But if you're just looking at the ball, the energy has to come from somewhere. So these are complicated ones, but this is as complicated as it's going to get. And it'll give a visual sort of representation of every type of energy we need to look at. So if you look carefully at the significant student learning outcomes, there's energy transfers and there's energy forms. So these transfers are ways of getting energy into our system, getting energy into our ball. Work's an example, we just saw that. Heating is the movement of heat. Electrical is a way of moving energy around, and light and sound are as well. And they take the form of these arrows, going into or out of our system. Energy forms, gravity, kinetic, elastic, all of these ones, they are energy bars. Right? And you can't have kinetic energy leaving the system, you can only just have kinetic energy. So the worksheet examples, there's another worksheet that has these ones. Again, this is as difficult as it's going to get, but it helps to explain with conservation of energy all of the experiments you could possibly do, all of the exam questions that could be possibly asked in a visual way. So this is the cart one. When you go to do the first worksheet example, the system is the spring in the cart. So when you look at it first, it has elastic energy because the spring is compressed before it pushes this cart out and it goes up. If you're just looking at the cart's just not moving there, it doesn't have any elastic energy. So that energy has to come from somewhere, and it comes from the spring. So this is one of the examples. I've made sure I've gone at 5 because I've got 5 bars here. And then I can get an equation from that. The work in is the kinetic energy plus the gravitational. I'm going to give you 10 seconds or 20 seconds to think about this one. I've got my hot cup of cocoa. And my initial state, it's really hot. My final state, it's cooled down. Right? What's going to happen here? You don't have to answer, just think of it in your head. So again, they'll say, hey, I thought energy's got a balance. Right? Well, the energy's obviously left the cocoa somehow, or the hot chocolate. And our 4 types of transfer are work, heating, which is the transfer of heat, electricity or light and sound. And this one has to be heat. Okay, so that heat goes out into the room. Now you could choose in the system, the room as part of the system. And then you'll have the thermal energy of the room starts low and then ends up going high as it slowly heats up a little bit. But this is a good way because this is introducing this idea of Q being thermal energy moved or heat. This is one of the ones that Kerry was talking about last week. You've got a kettle, you turn it on, so the water starts off cold, it ends up really hot. Where the hell did that energy come from? Right, and you can literally see the energy coming in with this cord here. That's electrical energy, and that can be calculated, right? With power equals V times I. So all of a sudden, if you can set this up like this for your excellence kids anyway, that are going to be doing the harder calculations, you can work out exactly how much electrical energy's gone in. You can work out, therefore, how much the thermal energy is increased by, but you're actually showing this. You're not just saying one equation equals another equation. And you've just got to get used to choosing that, because that's what we do in physics. We just choose equations. You're showing conceptual understanding. So that's it. You can use these energy bar charts honestly anywhere in this topic, from practicals to exam stuff. It makes it visible for your students, and I can't stress enough that it makes their thinking visible to you, so you can clearly see they understand or they don't understand stuff. And it forces conservation of energy into every situation, as opposed to just labeling things for the sake of labeling things. You can fall into a trap of just going through the process of we label energy, but there's no power in that. Forgive me for using the word power. The power or the use of energy as a physics concept is in conservation of energy, doing those calculations, and it forces it into every single situation, forces it into it. So even going back to the most simplest problem in an exam, which is drop a ball, you're given the height and the mass, can you find the final velocity, right? And the kids have to go through this process of rearranging to find kinetic energy. It's surprising how many kids don't realize why they're doing putting those two equations together. But if you're explicitly showing them that, or getting them to show you that, it makes it so clear to both you and them what's happening. So there's 4 activities, or there's quite a few activities in the NZOP that I've made that you can use with your class. The forms of energy, which I showed you, the transfers of energy, which I didn't show you, but it's a more advanced version of the forms. The energy bar charts, I showed you that. I showed you the energy bar charts and transfers as well. The FET simulation, the energy skate park, some of you may have found that already. That has bars. Universe and more is explicitly set up where you choose the system. So you click, I want this to be the system and this to be the system. And then you make energy bar charts, and it tells you whether you're right or wrong. So if you're leaving things out of the system, it'll force you to put work into the system, for example. And there's a practice exam that Kerry and I have worked on back and forth over the last few weeks. That's finished now, and it's just up to NZOP to put that online. I think the aim is that you use it as an in-class exam or as an in-class study aid for when you finally, when NZOP finally put a benchmark up. So at least you've got something that has some questions. And in fact, this practice exam I took last year's pilot exam and took a bunch of those questions and rearranged them so that they had visual forms of energy in them. And there's some other questions that I put there that I made myself. So I'll stop sharing my screen. And I don't know if Dave, there's any questions you want me to answer.
Well, a few people are saying, good job in the short version. Somebody was mentioning this, is there a parallel in chemistry for the conservation of mass in chemical equations? In the energy bar charts version of a conservation of mass and chemical equations.
Yeah. So, I mean, they could. So if you read the research on this, they sort look, bar charts are perfect for any scientific concept that has conservation at its core, right? So. And so I've now expanded them out, and I teach momentum with this, especially if you've only got momentum going in one dimension. So at level 2. Because you can end up having positive values and negative values because you have positive and negative momentums, right? And it's so good for showing these kids conservation. So conservation mass, absolutely. I'm teaching level 2 chemistry for the first time in 10 years this year, and they have energy charts that you have the activation energy and the reactants have a higher energy, say, than the products, but it's basically an energy bar chart, right? with just a little activation thing in the middle. And so our kids at our school have been using them for a while, these energy bar charts. It makes sense to go on to the stuff in chemistry, but conservation of mass, anything in conservation. Yeah.
It's a good point. Yeah, so any conservation, it's a tool to attack with. Brenda mentioned, could you use it for Lenz's law in level 3?
Yeah, that's a tough one.
Yeah, it is
I
a
have to
tough.
think about it. I mean, you could, if you attack Lenz's law from an energy conservation point of view, then 100% you could. To slightly change the subject, there's been a bunch of capacitor questions at scholarship level where my kids are really stuck on what to do, and we've ended up drawing energy bar charts, and they make sense.
Yeah.
The photoelectric effect, that equation, which I always just got used to seeing it as equation, energy of the photoelectrons is HF minus the work function. That's an energy equation, right?
Exactly.
And so that's literally an energy bar chart. You just draw it as an energy bar chart, and the kids get used to that as well. So all of these concepts can 100% be used at higher levels as well. So it'd be interesting to see if it ends up getting picked up at level 2 and at level 3, because it's the fact that my scholarship students use it, and I mean, you'll know if anyone teaches scholarship, and this will be the same in any subject, you can get some ridiculously mad algebra going on in the physics questions, but the kids don't know where to start. And so you've got these smart kids coming to these scholarship classes, and if you give them something like this, and they're like, oh, now, as soon as they draw it, they're like, oh, I see it now. And then they start plugging away at the equations and working through the algebra. That's not the bit that's tripping them up. It's the concepts on where to start.
Where to start. Yeah. I still remember being a first-year physics teacher in another part of the planet, and trying to convince kids, if you don't know where to start with energy, because physics is the study of energy. That's all we really do. But yeah, let's see what else we got in the chat here. Somebody's mentioning, is using an equal sign better than an arrow in your symbolic?
I would argue that it is, because eventually we're going to be substituting numbers into this, right? And we're going to be, gravitational energy to kinetic, if we're just putting that as an arrow, and then the next step is, well, what, why is half mv squared equal to mgh? So we're just going with straight to the convention.
Exactly.
The other thing is, you can get deep into the ontology and the epistemology of what the energy concept is and what it means to people. But it's not something that flows like an arrow. It's literally something that's there. You can count it initially, and it's there, and you can count it at the end. The fact that we're drawing it with an arrow means that we think it's some sort of semi-quasi-fluid that was in the ball, and then it flows out into something else, which kind of the Sankey diagrams lead to as well. And eventually down the line, when we get to level 2 and level 3, and anyone who goes on to engineering or physics, energy is not the stuff that flows. And so the arrow is kind of pushing towards that. So that's why the equal sign is, I think, is the way to go.
Exactly. Somebody's mentioning that they can't believe they've never used these things before. But they have seen Sankey diagrams many times, and getting bits of graph paper, the itty bitty tiny bits of graph paper.
100%, yeah, graph paper. Yeah, that's the only way you're going to manage to do anything. But I still find the kids really struggle to get where it comes out. I can get it where it meets, but yeah.
Let's see. Caitlin, that's quite a long question. You might want to actually, if there's a question in there.
No, I can see it. So, is there flexibility in the answers a student could give for their final energy bar charts? For example, the kickball, could a student give 1 unit of energy for kinetic and 2 for gravity rather than the other way around? 100%, right? So it's a qualitative understanding to make sure that energy is conserved. And I always stress, I don't know if it's going to have more gravitational or kinetic until I do the calculations. Remember, and I keep saying to kids, the energy bar charts are trainer wheels, right? When you were learning to ride a bike, you had trainer wheels that help you get to where you want to go, and were helping you balance and helping you learn to ride the bike. The energy bar charts are the trainer wheels of the equations. They're helping you to set up the equations. Eventually, you might not want to use them anymore. That's fine, but they're not the whole thing. So it's helping you set up the equation, and yeah. So I am a big fan of mini whiteboards, and when I say mini whiteboards, mine are quite big that the kids use. And say the one, the cart pushed by the spring and it goes loop to loop. So I do like 4 variations of that, especially in level 2. And we do the first one where it gets to the top and they all do an energy bar chart. And then we decide as a group, we say, okay, because we're going to do others on the same situation, we want to be consistent. Which energy bar chart do we like? Do we like the one that started with 5 energy units in the spring? Do we want this one that started with 4 or 3? And they eventually want to go with more, so they've got more ways of dividing it up. And so they'll say, okay, we'll go with 5. And so then once everyone's on the same page, then we go back to the second one. Okay, the cart only goes halfway up. Remember, we're starting it like Jimmy started it with 5 bars. And so then they all go and do the same thing from there. And you're going to get questions all the way through. You know, you've got a stick of butter that's sitting on the bench and it warms up. And it goes from a little bit of thermal energy to more thermal energy and it's melting. And they'll say, at what point does it melt? When it's got 4 energy bars or 5 energy bars? And again, you've got to answer this question. You know, that doesn't give us this information and we can choose how many energy bars it has. But they suddenly start getting into all these questions.
Exactly. You mentioned the one about heat way at the beginning of the chat. Matt asked a question about the arrow. Is it heat or heating?
Yeah. So it is both, but you've only got to use, I keep putting in brackets heating because people start calling the form of energy, what I've been clearly trying to call thermal energy, heat. So if you just banish that word from your vocabulary, you won't get it mixed up. But heat or heating, same thing, is energy leaving a system in the form of heat. So it's a verb, right? It's moving energy. Whereas thermal energy is the definition for energy that's in the cup of coffee.
Yeah.
So, I mean, that I can see that not coming back to bite us, but that being one thing that might be sort of revisited in a year, being like, that's too complicated, that distinction for kids. But my kids seem to have got it, even at a younger level. But it could be something that's looked at, but that's trying to distinguish movement of energy from just energy that's in an object.
Yeah, without falling into the conundrum that energy is stuff.
Yeah. I mean, the language we're using assumes energy stuff, right? And it's really hard to get away from that.
Yeah.
In the end,
sorry?
Yeah, in the end, energy's an accounting system, right? And nature's accounting system, they keep coming back to that. And so even though I fall into the trap of saying energy is the stuff that's moved from here to here and whatever, in the end, you've just got these numbers and the graph gives you those numbers and that's what you're trying to aim for.
Yeah. Matt, Mod?
So I just on the arrows that you had, the first one I think you had work, which is a verb, and the next one you had heat or heating, so that's the verb of that.
Yeah.
Then you had electrical energy as well. So is electrical energy, is that a verb as well? Because it's actually the way that energy transfers from one place to another.
Yeah, it is. It is. I mean, the word electricity or electrical energy is not a verb, but we're thinking about it as that now.
Yeah.
I mean, when you think about, you know, you don't ever take a snapshot of the energy and worry about how much electricity is in the wires.
Yeah.
Like we don't often, there's not an equation that we go straight to with electrical energy that's E equals. We go to power. We're talking about how much is moved per time, sort of thing. And so that's why.
I'm just teaching electric fields to my level 2s. So you could have a quantity of electrical potential energy.
100%.
That would be the bar.
100%.
Then the field is doing the work to turn it into kinetic energy.
Yep, 100%. Yeah. So there was a question last year of I don't know if you remember the exam. There was a set of plates and there was a charge in the middle of the plates. And there's my hands here. In one question it was moved up towards a plate, and in another question it was moved horizontal, right? And being able to show that in energy, but in the bar charts, showing that it has the same amount of electrostatic energy or electric potential energy here as it has here, no work is done. Whereas there's a change in the amount of energy that it has here, there's been some work done. Would have been such a simple way to answer that question. And no one invoked this idea of work. at all because they're not used to using work as a concept. Kids aren't. They're used to just using force times distance. Yeah.
Cool. Thank you.
Somebody has asked where the recording of this will eventually manifest. I know that the recording links have been posted repeatedly on Facebook by Helen from NZIP. And Matt, do you know if inside NZIP's website, there's also a list of links, or is that inside the government's website yet?
Sorry, I don't know. I know that Helen's been posting them. I would be surprised if she didn't have a document in which she was adding the links inside the NZIP as well.
Paula might be able to help us out. Go ahead, Paula.
I can just speak to the MOE's website. We have a link to the NZIP, but no links to the videos. So those are going to be hosted by NZIP.
Cool. So to answer the original question, where can you find a recording of the meeting? Inside NZIP's YouTube channel, there is a subset of videos. There's a subset of videos from Carrie about teaching energy. And then there's also a subset of these videos. Similarly, I'll bet you anything that the Chemistry Association is doing something similar, and NZASE is trying to house theirs. So if you were at all connected to the email network of science teachers, whether it's Mike's News or Facebook or whatever, just ask if you don't know where to find things.
Yeah, and then just searching NZIP on YouTube, get them as well.
Yes.
Yeah.
Any other questions? I'm trying to scan the chat here. Any other questions for Matt? I mean, we don't need to sit around here for another 20 minutes, really, but we're here for the people who are here. And if they have any questions about energy bar charts or the external in general, we can expand out the questions.
Yeah, I would just sort of summarize and saying, because they're new, start with the worksheets so you feel confident with them. And you'll see how the kids are either understanding energy or not understanding energy. And then once you start feeling confident, then you can start adding them into, hey, we're doing the experiment, we're boiling the kettle, we're putting the resistance wire in water, or whatever we're doing, and then start seeing if the kids can do the energy bar charts for those. And you'll get more confident and just be able to add it to every single situation yourself. But just start, be nice on yourself and start with ones that are already made. And you can Google these things, there's heaps of them online, but I mean, yeah, we've got some worksheets, so that hopefully will help you out.
I'll share my plan. I'm in charge of the year 9 unit titled Energy, which is, interesting in itself. But my goal this year is to fold in energy bar charts into the year 9 version so that it lays the groundwork for the kids in the future.
Right. Yeah.
And as well as, of course, use it in other ways. But there's no reason you can't start this early.
Can I give you some advice for that?
Yep.
Our year 9s struggled with the word system.
Yes, that'll be the biggest leap, I think.
Yeah, and so we just ended up changing it to the things we care about.
Yeah.
And then it all just fell into place.
Yeah.
Someone said we do a Rube Goldberg. So the trick is, and this is you changing your thinking, is you're looking at two states, an initial and a final. But you can look at the initial and you can look at after it's done the first energy transformation, right? Yeah, and then that can be the new initial, and then it can be, so you do a number of energy bar charts as it goes through this. But so many people are just used to doing one flowing list of labels that doesn't really tell you much.
Exactly.
Yeah.
Our year 8s, they spend a lot of time on the front driveway of the school doing those amazing things. Let's see what else we got here. A nice thank you thing. Yeah. Any other questions? Any other thoughts in general about the external before we stop the recording? Because it's sort of trickling off, I think. No? Okay, well, a few people are very thankful. And, well, before I stop recording, I should thank Matt for, he's been working on these things for quite some time, to put it mildly. And if you have any questions, I'm sure that you can reach out to him or anybody else, and we will try to do our best to answer your questions.
once again, yeah, thanks for showing up again. So it's a lot of work for all the teachers. They're having to, go to multiple of these, and then present them back. Friday mornings we have to then summarize them and present them back to our departments. And
Oh, wow.
yeah, all of the teachers are putting a huge amount of effort to make this work for the country. So thank you guys.